Okay, Pre-Cal 12, here we go. Let's get after it. We are looking at our section 7.3, which is solving trigonometric equations. So we're going to take a lot of the information we had in all of section 6, and then a little bit of section 7, but mostly section 6, and now solve for what angle satisfies this equation. Now, these are going to vary in difficulty. There are a ton of examples in the notes. I've only covered a few here, so if you want some extra detail, check the notes out, and you can always fire me a comment to see a video of one of the examples explained. So here we go. We are asked to solve sine 2x minus 1 equals 0. So when does this equal 0? And we're going to put our answer with respect to one rotation, but then we're also going to put our answer in a general form, which means with multiple rotations, because remember our sine waves, our cosine waves, they have infinite domain. Their period just repeats itself over and over again, so these answers will repeat themselves over and over again. Now, drawings in this case are going to help a lot, and special angles will and will not be involved depending on the scenario. So here's what we're going to do. It's relatively quite simple with respect to solving, but we've got to think about a whole bunch of different scenarios. So first, let's algebraically manipulate this so that we can isolate our sine x. So if we do that, we're going to add 1 to both sides, and then we're going to divide both sides by 2, and we end up that sine x equals 1/2. Now, first thing to identify is that 1/2 is positive. So my answers are going to exist in Q1 and Q2 because that's where sine is positive. So on our graph, I'm not going to make this to scale necessarily, but we're going to exist here and here. And if we have sine, it means that that's 1 and that's 1. It means that that's root 3 and that's negative root 3, but then that's 2 and that's 2. And that's not a unit circle, but that is our special angle triangle. So that means we have two solutions. We have a solution here in Q1, and then we have a solution here with the same reference angle in Q2. So if we look at that, what is my reference angle? Well, my reference angle is going to be 30 degrees or pi over 6. So my two solutions are Q1, and this is for part A. Q1, I get the answer of pi over 6. And then for Q2, remember I'm doing pi minus pi over 6 because it's my reference angle, so I get the answer 5 pi over 6. So for part A, in one cycle, I get those two solutions. But then what does that mean to be the general solution? Well, the general solution means every period rotation. So what we're going to do is we're going to take our two solutions, so pi over 6 and 5 pi over 6, and we are going to add an infinite number of rotations. So we add 2 pi n, and in this case, n is an integer. So what that means is, if n is 1, it's 1 rotation. If n is 2, it's 2 rotations. If n is 3, it's 3 rotations. N can be negative as well because it's just negative rotations. So that form of your solution gives you all potential solutions for this equation. That is called your general solution. Now these are going to get more and more complex as we move along, so this is a good first example. Okay, so second one. Now in this case you'll notice, wait a minute, I have cosine on both sides of the equation. So yeah, it's always going to start with algebra. You have cos x plus root 2 equals negative cos x. So what we're going to do is we're going to get our cos x together. I'm going to add cos x to both sides. And I'm also going to subtract root 2 from both sides. Because what that'll give me is 2 cos x equals negative root 2. And then I divide both sides by 2, and I get cos x is equal to negative root 2 over 2. And that might stick out in your mind. That is a special angle with a reference angle of pi over 4. Because root 2 over 2 is the same as 1 over root 2, right? So pi over 4. Now, it's negative. So that means for cosine, we are in quadrant 2 and quadrant 3. So this is why it's helpful to kind of do your due diligence, do your drawings. Where does this exist? Well, it exists here and it exists here. Again, not necessarily to scale, just doing it as a visual aid for you. So we got 2 there, we got our angles there, and those angles are the same. Now remember, these are our reference angles of pi over 4. So that means we're looking for that angle rotation, and we're looking for that angle rotation. So from here, we're going to get two solutions. We get a solution in Q2, which is going to give me pi minus pi over 4, which gives us 3 pi over 4. So that's solution 1. And then in Q3, I have pi plus pi over 4, which gives me 5 pi over 4. So that's solution 2. So those are my two solutions within the one rotation, within the 0 to 2 pi. And then for my general solution, cosine also has a period of 2 pi. So we have 3 pi over 4 plus 2 pi n, and we have 5 pi over 4 plus 2 pi n. And again, n is an integer. So you want to identify reference angles, special angles if you can, and then you want to identify what quadrant they exist in, and we find our rotational radian values, and then for our general form, we are adding the 2 pi n for cos and sine. Tangent's going to be a little different, and we'll look at one of those next. So here we have the question tan x equals negative or minus root 3 equals 0. So let's do some algebra here, and tan x now equals positive root 3, and that's root 3 over 1. So I don't have a graph here because I just want you to think about this one, right? Where does this occur? Well, that's my y over x, which if root 3 is my y value and x is my 1 is my x value, that means I have a 60-degree or pi over 3 reference angle. And tangent is positive in Q1 and Q3. So in Q1, I just get the answer straight up pi over 3. My reference angle is my angle. And in Q3, it's pi plus pi over 3, which gives me 4 pi over 3. So that is solution 1, solution 2. Now for tangent, our general form is going to be slightly different because the period for tan is not 2 pi. The period for tan is pi. And if you look at our solutions, we already have pi over 3, and pi over 3 plus pi gave us our second solution already, right? 4 pi over 3. And 4 pi over 3 plus pi is just going to continue the period rotation, of our tan wave. So we don't need plus 2 pi n anymore. In this case, we just have the one general solution, pi over 3 plus pi n. And again, n is an integer because our period for pi is smaller and that repetition occurs more often. So for pi, it is a plus pi n. And you'll notice here, those two solutions don't need to be given separately. I mean, it wouldn't be incorrect if you did that, but it's just redundant because pi over 3 plus pi is already 4 pi over 3. So you just get a redundancy there. So be aware with tangent. Now, we're going to step up our difficulty level a little bit. Obviously, things get harder and harder. And sometimes we need to consider multiple trig functions. So in this scenario, we have sine tan x equals 2 tan x. So again, first thing to do, easier to solve if we can set these things equal to 0 in many instances. So we're going to subtract 2 tan x from both sides. And now we can factor out a tan x. So we get tan x and then sine x minus 2. So if you remember just your basic principles of quadratics and factoring, what we get here is we get, well, when does this equal 0 and when does this equal 0? So first let's look at the sine. So sine x minus 2 is equal to 0, which means sine x equals 2. And if your alarm bells are going off or you try and plug this into your calculator, right, if you go x equals sine negative 1 of 2, radian mode please, you're going to get does not exist. You're going to get error 2 because sine doesn't exist outside of the value 1 and negative 1. So in this case, we can disregard this. We don't even need to worry about it anymore. And we're only interested in when does tan x equal 0. And tan x, remember, tan is y over x. So tan x equals 0 when y is 0. And y is 0 at 0 radians and pi radians. So again, the only solution we get in this scenario is, in one rotation, is 0 and pi. And then again, in our general form, you'll notice the only solution is given as pi, and you can see we already have a rotation of 0 to pi, so it's just going to be pi or 0, but pi n is the easiest. Pi n, where n is an integer. Because remember, 0 is an integer. So if n is 0, we're at 0. And that covers every potential solution. So every half rotation, we're going to get a solution. So that is one where we had to factor and look at two different values. And sometimes we will get solutions that do not exist. So here's another one. We've jumped into a secant function. And it's always going to start off with algebra. Now, in this case, you might look at this and think, you know what, that looks an awful lot like a quadratic. Because it is. You have a squared, then you have a similar term but not squared, and then you have a value. So this is exactly like a quadratic. Two numbers that multiply to -2, add to -1, and this is going to factor into secant x minus 2 times secant x plus 1. So in this case, we're solving for two potential solutions. We're solving for secant x minus 2 equals 0, which gives us secant x equals 2. And secant x equals 2, you might think, whoa, that's not allowed, it's bigger than 1. But remember, secant is the reciprocal of cos. So this is the same as cos x of 1 over 2. And it's positive, so we got to consider this in Q1 and Q4. Cos of 1/2 has a reference angle of pi over 3. So in Q1, we're going to get pi over 3, and in Q4, we're going to do 2 pi minus pi over 3, which gives us 5 pi over 3. So we have, so far, two solutions. And then we also need to look at our secant x plus 1 equals 0, which is secant x equals -1, which is cos x equals, well, 1 over -1, so still -1. Where does that occur? That occurs at x equal to pi. So we get three solutions. So those would be, those three box solutions are our three solutions for part A. And then for part B, since we were dealing with secant or cos, we have a period again of 2 pi. So we need all of these given. So we have pi over 3 plus 2 pi n. We have 5 pi over 3 plus 2 pi n. And then we have pi plus 2 pi n. Now, if you look really closely at these, they all differ by 2 pi over 3, but that's a closer observation. I would be just happy with you identifying that. You can see I touch on it in the notes a little bit further, but that's okay for this one here. So we have three solutions in that scenario. So we got a couple more to go. Here we are looking at a situation where, that's cosine, that's sine. How am I supposed to deal with this? Well, we go back to our identities. And remember that sine squared theta plus cos squared theta equals 1. So that means cos squared theta equals, or x, right, equals 1 minus sine squared theta. So what we're going to do is we're going to take this function, we're going to change this to 1 minus sine squared x, and then plus 3 sine x minus 3 equals 0. Water bomb in that 2 minus 2 sine squared x plus 3 sine x minus 3 equals 0. So now we have -2 sine squared x plus 3 sine x minus 1 equals 0. But we got a negative leading term, so let's multiply everything by -1. So now we have 2 sine squared x plus, or minus 3 sine x plus 1 equals 0. And now we have a quadratic we can factor. So we have 2 sine x minus 1 and sine x minus 1. So you can see we have two potential solutions. We have when does this equal 0 and when does this equal 0. So what we end up with here for part A, I'll try to keep part A down below, excuse me, is 2 sine x minus 1 equals 0, which means sine x equals 1/2. And where does that occur? That occurs at a reference angle of pi over 6, and it occurs positive in Q1 and Q2. So you can see everything is getting tied together here. So in Q1, we just have pi over 6, and in Q2, we have pi plus pi over 6, so, or minus pi over 6, sorry, so 5 pi over 6. So there's solution 1 and 2. And now we also have, when is sine x minus 1 equal to 0? And that is asking when is sine x equal to 1, and that occurs at sine x equals 1 at pi over 2. So we end up there with pi over 2. So that is our third solution. Now, from here, we can list those three solutions, and then for B, in our general form, we have pi over 6, 5 pi over 6, and pi over 2. And if you want just to look at it a little bit differently, pi over 2 can be written with a denominator of 6 as 3 pi over 6. And you'll notice those all differ by 4 pi over 6, which is 2 pi over 3. And if you added 2 pi over 3 to the 5 pi over 6, that's the same as 4 pi over 6. You'd get 9 pi over 6, which simplifies to 3 pi over 2. And if you were to, just to show you the rotation, if you were to add another 4 pi over 6 to 9 pi over 6, you get 13 pi over 6. And then you add 4 pi, you get 17 pi over 6. And our rotation continues and continues and continues. And then you get 21 pi over 6. And your rotation will continue all the way through. And you'll keep hitting your key points. But I'm, again, very happy if you just want to identify your 3 and add 2 pi n, 2 pi n, 2 pi n. It still shows that you understand the rotation. So as you can see, things do start to get a little bit more complicated, and it keeps going from here, I hate to admit. So I got one more here, and I want to demonstrate an example of one where you need to calculate using reference angles numerically, because we can't always calculate out our values with special angles. Sometimes we're going to have to just use our arctan, arcsine, arccos and calculate a decimal value. And there are an absolute ton of potential questions for you to try that demonstrate this. Basically, number 2, number 3, we have multiple letters, and they're worked through quite nicely in the answer key. So please feel free to have a look there. But if you would like to see a video of one, please do let me know. So in this case, we have 2 sine 3 pi. So we got a bit of something going on here. But then I also want to take the opportunity this time. Let's just look at one example where instead of 2 pi, we're going to look at it as degrees, just to give your brain half a break here. So first we need to isolate our sine. So we have 2 sine 3 pi plus 1 equals 0. What we get here is we get 2 sine 3 pi equals negative 1. So then sine of 3 pi equals negative 1/2. So what we know from there right away, and I'll write at the very top of the screen here, is we're going to be in Q3 and Q4 because we have a negative value, but we kind of got to hit a pause there for a second. And then what's our reference angle? Where our reference angle for negative 1/2 is 30 degrees. But since we're in Q3 and Q4, what are our two solutions? If we have a reference angle of 30 degrees, in Q3 we're 180 plus 30, so we get 210 degrees. And in Q4 we're 360 minus 30, so we get 330 degrees. Now, those look like lovely solutions, but the problem is they're solutions for 3 pi. They're solutions for our angle 3 times the size of our normal angle. So what we have to consider is we have to consider the fact that 3 pi equals 210 means that pi equals 70. We divide both sides by 3. But remember that we also need to stay within one rotation. And technically, we're only at a rotation for pi of 70. So now let's take 3 pi of 210 and we'll add a full rotation. Okay, we'll add 360. and that will give us 580. And if we divide that by 3, we get 190 degrees. So you can see that we're still within 360 if we consider pi, and not if we consider the 3 times theta. So if we, sorry, not pi, if we consider theta instead of 3 times theta. So we have to do this division piece. And since we're still under 360, we're going to go again, and we're going to add another 360 to the 580. Or sorry, 580 is the wrong calculation, 570, but the rest is still accurate. So we'll add it again here, and 570 plus another 360 puts us at 930, and it's like, yeah, that's way outside of one rotation, but with respect to just theta, if we divide by 3, we're still only at 310 degrees. So what you can see is you have solution, solution, solution for theta, and those are all acceptable because they're all within one rotation. Now, what we need to do, though, is we also need to take our original Q4 value, where 3 pi was equal to 330 degrees. And then we're going to add 360, because now we see we're going to do that twice. So we'll add 360 to both of those. So we get 690, and we get 1050. Those are going to be the rotations of 3 pi. But if we divide everything by 3, we get 110 degrees, which is within 0 to 360. We get 230 degrees, which is within 0 to 360. And we get 350 degrees, which is just within 360. So you'll see we actually have 6 solutions. Now, there is a little helpful hint for making sure we have enough solutions. And remember, it comes down to the fact that your period is equal to 2 pi over b. And in this case, what was our b value? Our b value was 3. So our period was 2 pi over 3. And if our period's only 2 pi over 3, and we're going all the way to 360, or in this case, our period would be 360 divided by 3, right, because that's 2 pi. Our period would be 120 degrees. If you take a full rotation of 360 degrees and you divide it by the period of our function here, because this thing is basically going to rotate faster than normal, we get 360 divided by 120 is 3. So we're actually doing 3 full revolutions. And if we are getting 2 solutions per revolution, we're going to have 6 solutions. And that's where these 6 solutions come from. So we have 70, 190, 310, 110, 230, and 350. Now, you could very well take your general solution and go 3 pi. This is where the general solutions get a little tricky as well, because our general solution is 3 pi equals 210 plus 360n, and 3 pi equals 330 plus 360n. But we don't want 3 pi, or 3, I keep saying pi, sorry, 3 theta. We want 1 theta. So 1 theta, you have to divide everything by 3, and you get the general solutions of 70 plus 120n, and then you get theta equals 110 plus 120n. So those will be your 2 general solutions. So everything needs to be divided by whatever factor of theta you have in your function if the theta or the x value is more than just a factor of 1. These are by far the most complicated and challenging questions, and there are a number of examples and also an absolute ton of practice questions. So these will be challenging. Give them a try. And again, if you have any questions, please fire it in a comment, send me an email, and I will make another little video to help sort of simplify this concept. It's not something you're necessarily going to grasp right off the bat. So thank you for this. We're solving our functions. We have our little quadratic tricks, we have factoring tricks, and we're considering our reference angles, and we're considering our quadrants. And then in certain instances, we're considering how many revolutions we have. But that only occurs if your x or your theta value is more than 1. So if you have 2x or 3x, then you're going to change the period, which changes how many revolutions you have in your 0 to 2 pi or your 0 to 360. So those are special scenarios you got to take in consideration, but these ones are quite straightforward. So thank you so much. Have a watch, probably have a watch again, compare the notes, practice, try. Don't get discouraged. You're doing great, and I will see you next time.